All right, hello everybody. I'm Will. I work for Typesafe, and this is video streaming for Play and Akka. So, if you were part of the workshop earlier on Monday, like first thing 9 o'clock, some of this will be familiar to you, but there are some extra bits which I've added, which are how to apply some of the things that we learned in Reactive Streams to Play and Akka specifically. So there's enough to show you different techniques above and beyond. First of all, I work for a company called Typesafe. My name is Will Sargent. That is my Twitter handle right there. We do Scala, Akka, and Play. I actually have a couple of T-shirts and some stickers available on the ground, and we also have a booth available downstairs, slightly to the left. And we are happy to hang out and chat and say hi. And Play, and we cover Scala, Akka, and Play. Scala is programming language. Akka is the messaging framework on top of it. And then Play is, on top of that, the web framework that allows you to do things without having to tie yourself up in knots, is the way I usually describe it. But more than that, Typesafe is a reactive company in that a lot of what it tries to do is build out software such that it provides resources necessary to the demand, and not more than that. And what Reactive breaks down to is 4 different platforms, 4 different principles. The principle that you have something that's responsive, that when you actually click on something, then something happens, but not before. It's not wasting resources polling. It's not keeping a lot of memory and CPU in the background. It's resilient. That means that if something crashes, then it brings itself back up. If something goes wrong, then it knows how to recover from it. If you are in a situation where you are having the system go down and then somebody has to press the button or like jiggle something, that's not resilient. You need a system which is available even under the consequences of failure, because enough times, if you get big enough, if you have enough happening, something somewhere is going to fail. Machines are just unreliable in general. It is elastic. That is, when you have demand, then you have the system scale up to meet it. When you don't have demand, then the system can scale down so that it does not have to waste resources on requests that never come in. And then finally, it's message-driven. So we have the idea of responding to messages that are immutable and passing messages between systems, and not carrying a whole lot of state around, not carrying a whole lot of immutability around, instead holding to the idea of events as a way of representing state changes. So on top of that, we have something called Reactive Streams. Well, what are they and why do we need them exactly? Well, you have to be able to handle data, and you have to be able to handle a lot of data coming in a lot of the time. And the big problem that a lot of people have is that when data comes in, you can have a lot of data a lot of the time, and potentially a lot of data all of the time. Think about YouTube, think about Spark, think about all of these different companies that they take in streams of data, but these streams could go from megabytes to gigabytes, potentially within a very short period of time. Think about the amount of scale that Twitter has to go through in any kind of news event, spiking their load almost instantaneously. You have to be able to create a system that can respond to that. And you have to be able to have a system that is able to take that as a series of messages and be able to work on something and then pass it along to something else, not keeping any state around, not having a heavyweight process it, just have something take a piece of data, work on it, and then pass it out, and then shut itself down cleanly. So Reactive Streams are the implementation and the interface behind that. So they give you a non-blocking data flow where everything that you use is actually being run by a stream. But when you're using that stream, you are only paying for the costs of CPU time while you're processing the message. It doesn't hang around in the background. It's an ephemeral flow of data. You're not looking at the data and bulking through it initially. It gets handed to you and then it goes back out. And then because you're only dealing with the data as it comes in, you are only going to know about one message, one incoming message at a time. And it's up to you to be able to say, I want to keep more state around internally and handle that. So it describes the transformation of data as well. So there's a number of use cases which I've already described. Batch processing, monitoring analytics, anything where you have real-time consideration, anything where you want to be able to handle data as it comes up immediately. So when we talk about publishers, when we talk about Reactive Streams, we're talking about publishing and subscribing. And this comes back to video processing especially, because when you're actually playing a video, you're actually demanding a fair amount of data coming in, and you're demanding a fair amount of data coming out. But that data and the amount of data that can be returned to you is going to come in the form of a demand from the subscriber, the guy who's actually watching the video, and the publisher, the one that's actually transmitting these streams of video to you. So within that, you can imagine that there's quite a lot of wriggle room between what the subscriber asks for and what the publisher has to send back. So there's a dynamic push-pull behavior here, where if you have something that's listening for a stream of data, a video stream of data, potentially, then you can have either the push or you can have pull. So both of these work in different circumstances. Push works when the consumer is faster than the producer. When you actually, it's faster for it to like tap on the door and say, hey, I'm ready, give me some more data. And then pull is when the producer is faster. The producer has like an internal queue of work that's piled up behind it. And then the consumer is just going to say, oh, I'm just going to pull things off of this queue immediately because I know that it's stacked up for me. And that happens behind the scenes. That happens automatically. It's just not something you need to worry about. The implementation takes care of that for you. So data flows downstream, demand flows upstream. Between that, nothing happens unless there's actually a demand for it. So you don't have to spend a lot of time thinking about the internals of it. You just need to make sure that you're writing out your code according to when there's a demand, and the rest is handled underneath the hood. And that is a different, that is the repeat slide. So there's 4 pieces to it. There's an API, which is very simple. You just have publisher and subscriber, and then you have a subscribe relationship between the two. You have the SPI, which is the Java interfaces for implementations. There's a number of companies doing that. You have the test harness, which is used to make sure that everything works correctly between them. So you can actually swap out different libraries that provide the Reactive Stream implementation for you. And then finally, there's a specification website where they mention everything that you're doing there, everything that the Reactive Streams API is supposed to be doing, and keep people updated on what libraries are doing what. So this is the API. And you can see it's very simple. You've got publisher and subscriber, and then you have a subscription, which is happening in the middle, which, no, that's not a subscription, that's actually a subscriber. But that creates a subscription underneath the hood. And then when you have that interface available, it only defines 3 things. There's onNext, which is the next element, and then there's 2 conditions that will close down the stream. OnComplete, everything worked fine, the stream is gone. OnError, something didn't work fine, the stream is gone. But that's basically it. You've got the subscription itself, but that only says we want some number of elements. It doesn't do a lot in terms of defining flow control or anything else on top of that. And there's a number of companies that do things with that API. Obviously, Akka Streams is the Typesafe implementation, but there's also the non-blocking implementation by Netflix, RxJava, Pivotal Spring Reactor, Vertex by Red Hat, and Oracle itself has some involvement in it as well. So that's enough verbiage for now. that tells you what reactive streams are. Now let's actually show some code as well, because I want to be able to display how simple it can be to write. Here we go. Okay. So I have two projects up here. One is Reactive Video. The other one is a Streams workshop. This one shows you the file here. So you have an actor system. You have a file that you're reading in. You have an FFmpeg encoder that's being played through. And then you have a subscriber here, which consumes frames. And this is the provider. You have the publisher here, which provides frames. So given this relationship here, let's see what I can actually do with this. This is exercise 1. Thank you. So you can automatically have a video subscription. So this is, that's falling off the edge of the screen. So this shows you immediately, we've got a publisher of frames and we've got a subscriber of frames, and we can already take the video, we turn it into an AWT buffered image, and then we blitz it to the screen under a Swing application. So that shows you the power of Reactive Streams in a nutshell for what really matters to the internet. So So that shows us here, we've got a frame publisher, and you have a file, you read it in, you have a publisher. Here you have a subscriber, same thing, comes straight out. This is all you have to worry about. You don't have to worry about the underlying implementation. You don't have to worry about any kind of technology that it's using. The only thing you have to care about is that it implements this interface. And the demo I've already shown you, but Akka Streams is where we really get interesting, because this is where we start playing around with state, and this is where we can start playing around with implementation. So Akka has an implementation of Reactive Streams, and in fact, you already saw it. It was underneath the hood. But what it does is it converts publisher and subscriber into actors and actor messages and methods that are available to be called. So doing this, it allows you an integration that is message-based, that is resilient, that is reactive in all of the forms we discussed earlier. Here's how you create an actor and have it be a subscriber. So here's something that takes any element that you pass in and just prints it out to standard output. And this is the entire thing. This is the whole code. There's a message here that is special, which provides the element itself, and then there's a request strategy which handles how it processes incoming messages. But then after that, you have a wrapper, actor subscriber, around the actor, which provides that subscriber interface for you. And the same thing for Akka Publisher. Actor Publisher, when you look at this, you have a publisher message, you have a request, you have a total demand which says how many messages should I send out? And this is dynamic. So as you call this, it decrements. It's actually a method, not a variable. And then it gets instantiated and wrapped in just the same way. And all this does, you can see it prints out 1 as a message. So it's a publisher of int. So when you put the two together, you can say, I have an int publisher and a println subscriber. You stick those two together using subscribe, and it will just print ones out down the screen for the rest of the time. So the question is, why actors as publishers? Well, they're smart. They can do things that you wouldn't anticipate. They can be able to buffer internally. We'll talk more about that. They can spin up child actors and be able to distribute load. And if you have Akka clustering on top of that, then you can distribute nodes across, you can distribute across nodes, which are different machines potentially. And if you start putting Mesos into the mix, then you can start provisioning extra nodes as well and really blow the thing out. So again, you're dealing with messages. As long as that message gets processed, it doesn't really care where the message came from. So you can send something to an actor. An actor can send something out all the way to the end of the world, process it, come back, send the processed message, and you're fine. You have no idea that anything happened. Not only that, they are resilient in that when they crash, because everything crashes eventually sooner or later, they discard their internal state by the supervisor that is given to them, and the supervisor restarts them fresh, so that when you're actually starting up a new instance of the actor, if something goes wrong and you have an internal state that's corrupt, it will just throw it away and create a new copy for you. So you won't have to worry about, oh God, how do I reconfigure the system, or how do I pull things up? That's already built into the idea of letting it crash. So the next thing we have to worry about here is backpressure. Backpressure is a complicated topic because what it means is different things to different people. And there's actually a difference between backpressure I/O and backpressure on TCP and backpressure from the whole application. That is, backpressure is more of a concept than it is a specific implementation. You can't simply say, well, I put backpressure in my TCP stream over here and therefore I'm good. Well, you can still have the system as a whole overloaded and need to push back because its CPU is too high or its memory is too high, and you're going to run out of some resources somewhere. So backpressure is something that is being tackled in a lot of different areas, but the basic idea is that when you have a downstream consumer and it can't process the message fast enough, then it is able to push back on the producer to say, I can't handle these many requests. Stop sending me so much data. So reactive streams consumers stop requesting more elements until they're ready to process more, and consumers only fire if there's demand. They don't try to send messages if they aren't actually asked for, and so it allows some elasticity to the system, where only the messages that can be processed will be processed. So because you're doing this, and because you're doing it right from the very beginning of your pipeline, hopefully, you can say, I want to spread my demand through the entire system. You can say, I know where it is that I'm starting off, and I know where the hotspots are, but I am not going to have anything back up. Because eventually what happens is, if you're dealing with an infinite stream of data, you only need one bottleneck in time to really blow the system out. If you have an unbounded buffer somewhere, and everything will just lie in that buffer and keep adding to that buffer one by one, all you need is enough data and time, and eventually you'll get an out-of-memory exception. So you should be able to limit the number of in-flight messages. You should be able to bound the amount of memory and bound the amount of CPU that you're processing, and not deal with more than you have to, and don't use unbounded buffers. So we can do some amount of buffering by making sure that if we are asked for one element, and we know that it's really expensive to process one element, but it's equally cheap to process one element or 100 elements, which is typically the case, there's this thing called mechanical sympathy, which says if you're dealing with data that comes in if you're dealing with data that comes in and the CPU has to deal with it once, the CPU can't take advantage of cache prediction. It can't optimize for the general case. Hotspot doesn't get used. And so one of the things that you can do is have a provision for smart batching, which says, you know what, when we get these things, I'm going to store these up, and then I'm going to process them in batches of 10. And that will actually ease the load in my CPU, because the CPU will be handling it in mechanical, the system will be handling it in mechanical sympathy with the CPU. So we can ensure that there's no sputter. We can ensure that the well never runs dry, because we always have packets available to hand out. And we can also use, to pull faster than the downstream consumer, which can be useful as long as we know that we're not pulling too much. So when we get to Play, Play already has facilities for streaming data. And this is one of the things that makes Play so attractive, is that it is able to do two-way WebSocket traversal. It is able to do things with iterates and numerators. It is able to stream data through chunked encoding. And all of that is built into the framework and has been since 2.0. And so Play is very good at dealing with packets. Play is very good at dealing with large streams of data and processing gigabyte files and potentially uploading gigabyte files as well. But there is a problem with them, is that iterates and enumerators are fantastically complicated. And unfortunately, Play's iterate implementation is complicated even by iterate standards. And so, and so there is kind of the problem where, yes, you can do this using iterates, and yes, you can actually put together your own iterate models, which will allow you to stream data without any kind of overhead and do it in a reactive fashion. But a lot of people have problems with that, because you need to understand the concepts first. And Reactive Streams handle that for you. You have a publisher, you have a subscriber, you call subscribe, you're done. So, Play 2.4 has experimental streams, and what it does is it plugs the existing architecture, futures, promises, numerators, iterates, and it puts wrappers around them to convert to and from publishers and subscribers. So I downloaded the master snapshot and compiled it last night and verified that everything was working correctly and played around with it some. And one of the things that's interesting is that this is the whole method. If you are streaming a video through Play, you see here we've got the read file. The read file is exactly the same. It's simply a frame publisher. But then here, we're converting this to an enumerator, which is a source of frames, much the same way that a publisher of frames is. And then we have something that maps these from frames to bytes using this encode frame method. And then once we set that up, once we set this up with this map function, then we can stream this chunked video stream with some headers saying it's MP4 and there's no cache. And then we can play video. So let's try that out. Activate will run. And let's move to the reactive video here. There we go. All right. And now we have video streaming. And you can, oh, good grief. All right, there we go. So this is using VLC. VLC is going to localhost 9000. It's using a local stream, and it's just downloading the data and then streaming all of those frames through the stream that we saw earlier. And that gives us video streaming with play and Akka. And it's kind of a shame that you can't hear the audio here because it really is interesting. So that shows us how to stream video through play. And we'll show you, this is the application here. And then one of the things that's going to be interesting is, all right, so let's go back to the slides and so the frame publisher itself is where we actually start having to deal with the consequences of pulling in that data and asking where it comes from. So each frame here contains 8K of data. There's an internal buffer that the actor has, which says, all right, when we pull in data from somewhere, we're going to pull in 100 frames at a time. And then whenever anybody asks us for frames, we're going to pull them out one at a time. And then the buffer, if it's empty, then we fill it up to 100 again. And then we start playing it, counting down from 100 internally. So the source of the bytes here, I'm reading from a file, but you can actually pull this in from Zencoder or from Amazon or from FFmpeg transcoding. And the next thing that's interesting is, all right, well, why do we need a buffer? I mean, it's asking for one frame at a time. Can we simply just like read in one frame when we need it and then pass it along? And so, and then the next question is, well, all right, what is the overhead? Is it asking for like 10 frames at a time, 100 frames at a time? And what's the CPU overhead to that? Is that something which is costing a lot of memory, a lot of CPU to actually process all of this data? So we can actually answer some of that. So let's take, here we've got the buffer. You can see that. And the buffer capacity right now is 100. Let's move it down to 1. And let's make sure that we have logging enabled on this thing. All right. And now, stop this guy, and then start it back up again. So you see that it's compiling, and you see that the buffer size is 0 every time, and it is reading in elements. The total demand is 1, and so the enumerator is always reading in one buffer at a time. But look at how many times it's doing that. It's doing it pretty much every single microsecond, so it's doing it a lot. And you can see it's sort of keeping track here, and there's not that much memory involved. But at some point, it does start to run dry, and then it eats up CPU like you wouldn't believe, because unfortunately, one of the interesting things is printing out all of these logs to iTerm actually has a significant overhead and causes significant CPU. So I try to cut down on some of that, but you can see like it's going through 300 frames, 350 frames. It starts getting messy. But you can see it's actually keeping up fairly well here. But I don't like doing that. And then you can actually see here, one of the things that we can do is we can up the buffer contingent. We can say 100 here, and we can say, all right, if we're loading from a buffer, you see the total element sizes and the buffer sizes here. All right, well, let's see what happens with the buffer. Let's see what sort of behavior we get out of it. So let's clean this. And you can see here that almost immediately you can see it goes 0, and then there's 99, and then it starts feeding its way back down to 0, 3, and then it starts popping its way back up again. And it's happening really, really fast here. So we can actually cut down on the amount of logging by doing a mod 20 or a mod 50 or something. But the more buffer you give it, the less it has to rely on the producer that is handing it those particular frames, which are 8K each, and the more window you can have in between it handing you something and you having to hand something back. So that's why Akka publishers are useful, is because once you do that, you have that much more window in terms of figuring out, oh God, my transcoder is slow. Can I move down to a lower encoding rate? Oh God, my transcoder is slow. Let's bring up some more resources and start distributing this load more. Or even just like, let's increase the size of the buffer. I mean, if we're getting asked, if our buffer empties out like every 2 seconds, obviously our buffer isn't big enough. So we may have an upper bounds, but we may only want to increase that bounds when we get hit often enough that it's worth doing. And here you can see, yep, now the CPU is tanking, and now you start seeing tons and tons and tons and tons of requests. So, yeah, at this point, you usually have to kill the thing and start over. Or you can wait for it to scroll. But having said that, if you turn off logging, and if you turn off if you turn off the info logging and you have a buffer, then the overhead is basically the only overhead that you get is you're reading a file or you're reading in some packets some of the time, and then you have the buffer, and the buffer is in the memory only for as long as it needs to be. So again, one thing that's important is that we have an array blocking queue, a good bounded buffer here. We don't care about the concurrency aspects. We are actually buffering from a stream internally here. There is actually another one called Zuggle, but that turns out to have problems. So I tried doing some dynamic transcoding last night. Didn't exactly work all that well. But the basic principle is the same, is that when you have data, and when you can process that through actors, then you can start doing things with your transcoding scheme, with your transcoding code and your transcoding architecture that simply wouldn't be possible otherwise. So one of the things I mentioned before is just-in-time transcoding. That is, as soon as you upload a file, as soon as you're transcoding it, you can start playing the stream back. It'll go through and it'll transcode things, and then it will hand back frames to you, and you take those frames and then you send them back on to somebody. So you're not wasting resources transcoding something in advance. You're only transcoding it as somebody actually needs it, and just before it happens. And once, of course, you do that transcode, you can actually send those bytes any way you want. You're not necessarily limited to like reading it from a file system or going back to a CDN, etc. You can actually pass those bytes and those frames around inside your system any way you feel like. You can encapsulate your provider, so you can actually have 2 different transcoders running at the same time and have scatter-gather. So you can have Amazon and Zencoder running these things side by side, and then being able to pick which one is actually going to work. So if one fails, you do a failover automatically. You can actually alter video streams on the fly. You can inject frames, you can adjust frames, you can change the transcoding quality. And then finally, you can also, because they're just binary data, you can use WebSockets with Play. That's one of the great things about it, is it has full, probably best WebSocket support I know of, actually. But it has concurrent broadcast in order to be able to share binary streams of data across everybody who's hooked into a WebSocket connection. So the same way that you have a chat room and you're talking to people and you're typing things in, then you can send frames of video around to people and have little clips or have animated GIFs, etc., and be able to deal with them in exactly the same way. There doesn't have to be this distinction between textual data and HTML, and binary data, which is being done on, some dedicated piece of machinery. You can actually handle everything through Play and through streaming and be able to deal with it on a much richer basis. Okay, so that about concludes things. I think we're wrapping up a little early. So next thing up is, does anyone have questions? And yes?
You were using FFmpeg, and this is like a C library, right?
Yes.
Can you tell me which wrapper or what that was you're using there?
Yeah, there's actually there's a library called Zuggle, which is a Java library on top of FFmpeg. And I believe that there's another one called Humble Audio or something like that, which is, it's a guy called Art Clark, and Humble Audio is his try to make it a little more Java-like, because right now you have to check return codes instead of throwing exceptions for things like that. Yes?
Do you have experience with, I mean, I know you're partial to Play, and of course,
Yes.
but do you have experience with other message passing, message stream-based web servers like Mongrel 2? Or can you speak to differences in performance and behavior?
All right, so the question was, do I have experience with other streaming or messaging frameworks other than Play and Akka? No, but I did work for a transcoding company at one point. And so we actually had to deal with, it's a company called Topspin Media, and we had to transcode all of the musicians and all of the videos, etc., for all of the music videos especially involved, and then be able to sell them and be able to bundle up that music. So we did quite a lot of video transcoding and audio transcoding, Nine Inch Nails being the biggest one probably. Yeah, that was a lot of work. In terms of, you said that there was a particular company that you mentioned, Mongo?
No, the open source project Mongrel 2.
Mongrel 2. No, I have not heard of Mongrel 2. I mean, I mean, I know of a Ruby web server called Mongrel, but I don't think that's it.
Author, but language agnostic, and because I mean, with Play you're on Java and Scala, which is good for many things, but sometimes you want to embed other.
Yeah, no, the API itself, Reactive Streams, is a Java API. So all of the languages and all of the companies that are implementing that API are by definition using Java. Having said that, I honestly believe that it is the best option available if you want to do heavy processing in a lot of cases. Because when you look at the overhead of using Ruby or using any kind of raw C++ mechanism, well, they kind of have two problems. There's one, Ruby is single-threaded and kind of top-heavy on top of that. And two, if you're using C++, yes, it's very fast and effective, but the error handling and the resilience is very difficult to plug in. And then, of course, it's kind of brittle after that. So, I mean, that's just my personal opinion, but, and I'm not specifically labeling it to Typesafe, but definitely I think JVM platforms have the ability to be flexible and be able to be fast and powerful at the same time too. All right. Yes.
Is it possible in the publisher to monitor things like network load to decide if you want to
Yes.
stream at a lower quality, for example?
Yeah, that's an excellent question, and that's one that actually gets to a more fundamental issue, which is how do you? I mean, when you're handling backpressure, then you can have backpressure of a stream. But as I discussed earlier, backpressure is really an overarching concept, is that if you've got an Akka cluster, for example, Akka clustering has a feature which is called adaptive load. And what that does is it tries to make sure that the next request will go onto the lightest loaded node. So in order to do that, it has to use a performance library called Cigar, Hyperic Cigar, I think, which monitors the load on each individual node to see which one is heavily loaded, which one is lightly loaded, and then try to associate it on that bounds. So one of the things that you have to deal with is, in order to know what to do, you have to be able to see what your overall load is on the system. And if somebody else can do something about it, then maybe hand it to them. If nobody else can do something about it, then maybe you want to fall back to that. So that isn't in Akka itself, that is in Akka clustering. And Akka clustering has something called a metrics listener. And what the metrics listener does is it takes all of the nodes, well, okay, it's something that you put on each individual node that tells you, okay, I'm under heavy load right now, do something about it. But you can take all of the events, again, those messages are passed around inside of Akka the same way anything else is. So you can specify a listener, you can aggregate all of those messages onto a cluster singleton, and then you can say, the system as a whole is under load. I want everybody to start doing things at half strength. And that way you can have a more even experience. Or you can deal with things individually and say, I want this particular server over here to like cut down on things because it's kind of wobbling on the edge and it has a tendency to crash. And that's kind of good for like, what do they call it? Catastrophe events, where like you get fine up to a certain point, and then if you go beyond that point, then like running out of memory, you hit swap. It goes from just about struggling to really not doing well at all. And so dealing with those kind of events, even though the system may technically be capable of processing, you may want to give it some window room before it hits that point. And so yeah, you can deal with that, but that isn't necessarily to do with reactive streams necessarily so much as it is to do with the idea of backpressure in general and how that relates to monitoring. I'm not sure if that answered your question, but okay. All right. Anyone else? Excellent. All right. So we have a booth, as I mentioned. We have T-shirts, and we also have stickers. All of them are freely available downstairs. And if you would like to talk to me or Lund or Klaus, who is also available, then please hang out at the booth. And also Dick Wall and Adrian will be giving talks later on today. So please see them and give them a big hand. Thank you very much.